Hello, everyone. My name is Andrés Cristi. I'm a postdoc at the Center for Mathematical Modeling at Universidad de Chile. Next year, I'll be joining EPFL, and today I'm presenting this joint work with Jose Correa, titled A Constant Factor Profit Inequality for Online Combinatorial Auctions. In our problem, we have a set M with M items that we want to allocate to a sequence of agents that arrive one by one. And these agents have independent valuations for the items drawn from certain known distributions F1 to Fn. And these distributions are supported in certain set of monotone and subadditive valuation functions. Now, I'll tell you in a couple of slides what subadditive means, but I want to make clear here that these valuation functions are not just a single number for each agent, but mappings that take subsets of the items and give us a value for each subset. So each agent has a valuation function that maps every subset to a value. Now, importantly, these valuations are independent across agents, but for a given agent I, values for different sets are arbitrarily correlated. Now, what we want to do here is to allocate these items to these agents in order to maximize the expected social welfare we obtain. And we want to do this allocation on the fly. That means whenever a new agent arrives, we want to decide immediately which items to give to this agent, and this decision is irrevocable. So the first agent arrives, we observe the valuation function V1, and we want to decide immediately which items agent 1 gets. Next, we receive valuation V2, and we want to decide from the items that are still available which we will give to agent 2, and so on and so forth. And then what we want to maximize is this expression. So if we have an algorithm that does this decision on the fly, and we call alg I the set that agent I gets, we want to maximize the sum over all agents I of the valuation BI evaluated in the set alg I. And this expectation is taken over the randomness of the evaluation functions and all the randomness that is introduced by the algorithm. Now, we want to maximize social welfare, and we want to compare the social welfare we obtain with that of the optimal offline allocation. That means the best possible partition of the items for this objective function. So, and we also call it the profit social welfare, because if a prophet that can see the future decides, the prophet, since he knows the future, will choose the optimal allocation. So that's why this is called the profit inequality, because we want to compare what we can do online against what a prophet can do, a prophet that can see the future and can do the best possible allocation. Again, we consider the expectation here, where the expectation is taking over the randomness of the evaluation. As I said, we restrict ourselves to the class of subadditive valuations, which, as the name suggests, is the class that satisfies this inequality. For every pair of subsets A and B, the value of the union of the two sets is at most the sum of the values of the separate sets. This is also known as complement-free evaluations because this condition rules out complementarities between the items. So, for instance, evaluation that is not allowed is value 1 for the entire set and 0 otherwise. This type of evaluation is not allowed in this class. And this is a natural class that arises in several situations and has been studied in different settings by economists and computer scientists. And it includes several other classes, such as additive, XOS or fractionally subadditive, but also submodular and gross substitutes valuations. Now, as I said, this type of problem has been considered in different kind of works and different variants. And I want to mention a few results. First, of course, we could consider the offline problem, just the plain optimization problem of maximizing the social welfare if we are given the evaluation functions. And we have this theorem by Feige that says that a 2 approximation is possible in polynomial time. And another natural question is, what if the evaluations are not public information, but instead they are private information of the agents? So we have an offline problem, but we have a game theoretic setup. Each agent observes his or her own valuation function and then interacts with a mechanism that decides what's the allocation. And here the result is as follows. We can run m simultaneous first price actions, 1 for each item, and the equilibrium in this game is a 2 approximation. So again, this game works as follows. Each agent submits a bid for each item to the mechanism, and then the mechanism used in these bids just allocates an item to the highest bidder, and this results in an allocation, and the game has an equilibrium, and this equilibrium is a 2 approximation. Now, back into the online setting. Prior to our work, there was a 2 approximation for a restricted class known as XOS. This is a subset, a strict subset of the subadditive evaluations. An interesting feature of that algorithm is that it uses posted prices. That is, we just set a price for each item at the very beginning and then let the agents take whatever they prefer. And for the more general case of subadditive evaluations, prior to our work, the best known factor was an O of log number of items. And interestingly, this O log m approximation used also posted prices, setting a price for each item at the beginning and then let the agents take whatever they want. And if you look at this picture, we have several constant factors here, but for subadditive online, we have a log m. So it was for a long time an open question whether a constant factor was possible in this setting. The best impossibility result we have is just a 2. So the gap was between 2 and log m. So it was an open question whether a constant was possible. And our result is that it is in fact possible to do a constant. We gave an algorithm that is a 6 approximation for the class of subadditive evaluations. And it uses techniques that are very different from the two other results we have for the online case. In fact, if we wanted to use the same approach, we have two problems. If we wanted to use the approach for the two approximation for XOS, we have that XOS are a bad proxy for subadditive valuations. XOS valuations cannot approximate subadditive valuations better than a factor log m. So if we wanted to use that approach, we immediately lose a factor of log m. Now the log m, because of this, uses a different technique. But the authors of that work show that in fact their analysis is tight. So their techniques cannot be used to get a constant. So what we do has two parts. We use an idea that comes from sample-based profit inequalities. That is, allocating using only samples instead of known distributions. And the other idea is a fixed point argument that is basically derived from the result that says that when information is private, we can run a mechanism that gets it to approximation. So we use that result and we combine it with an idea from sample-based profit inequalities. Now I want to give you some hints of these ideas that allow us to get this constant. And the first idea from sample-based profit inequalities is based on this very simple observation about IID random variables. If I have two IID copies of myself and they have a fight, each of them, since they are IID copies, will win with equal probability this fight, right? So if I fight with an IID copy of myself, I win with probability 1/2. This is a very basic and obvious observation, but this is very important for an analysis. Now, to exemplify this idea, let's consider the case of a single item. This is the basic profit inequality problem. We're trying to allocate a single item to a sequence of n agents that are values drawn from known distributions. And I will run this algorithm. I will draw a copy, an IID copy of each of the agents. I will call their valuations V prime, V1 prime to Vn prime. And I will set as a threshold the maximum of these sampled values. And then when I get the true sequence of values, I will just give the item to the first agent whose value is larger than the threshold. So in other words, I'll create a fake world sample with the same distribution as the true world, and I will wait until an agent from the true world beats the largest valuation in the fake world. Now, it's clear that the value of the agents that beat this threshold is at least 1/2 of the value of the maximum. Because the maximum always, I mean, if the maximum beats the other maximum, then we get a good value. And this happens with probability 1/2. Now, the problem is that maybe the item is not available when the true maximum arrives because a previous agent beat T prime. Now, we can easily observe that only with probability 1/2 this will happen. And why is that? It's because of the following. Let's consider an agent whose value is larger than the threshold. We can say that it's harder than in the real algorithm that agent I gets the item than in a situation when there is an IID copy of agent I before I. So I'm just adding an extra copy of the agent. So it's now harder for agent I to get the item because we need that the item is available. So now it's easier than before that the item is allocated earlier. And now let me call T double prime the maximum of the values of all other agents, including this fake copy of agent I. And notice that now T prime and T double prime have the same distribution. They're just the maximum of one independent copy of each agent. And the item is available at the end if T prime beats T double prime. Since they're IID, T prime beats T double prime with probability 1/2. So the item is available half of the time that VI beats both thresholds. Now, the previous algorithm gives a constant factor. I didn't give you the full proof, but a glimpse of it. And we would like to do this for each item. We have M items. We would like to repeat this analysis for each item. And the problem we have, because we have these valuation functions, is that we don't have a per item value. We have a per subset value. And we would like then to translate our valuation function that gives a per subset value into per item value. As I said before, these subadditive valuations cannot be approximated by XOS valuations, let alone by additive valuations, per item valuations. This is a tricky question. And what we can actually do is to use the bits from the result I mentioned earlier in the talk. Remember, the result was if we run simultaneous first price actions for each item, the equilibrium of this game is a two approximation of the social welfare, for the social welfare. So let's look more carefully what this mechanism is. We're asking each agent to submit a bid simultaneously, a bid for each of the elements for the items. And the mechanism takes all the bids and gives each item to the first price, so to the highest bidder, right? And what is an equilibrium in this game? Notice that each agent receives his or her valuation function as private information. This is a value per subset, but the bid is a value per item. So internally, each agent in an equilibrium has to translate his or her valuation into a per item value, per item bid. So an equilibrium is actually what we are looking for. An equilibrium of this game is what we are looking for to implement the other algorithm. This is, in fact, a translation between valuations that are subadditive and per item values. This is, of course, a black box transformation because the equilibrium is just a fixed point, and that's why we call it a fixed point approach. It's not an explicit formula for translating valuation into numbers. But now that we know that this equilibrium exists, we can take that and apply it to the previous idea. And we call these random score generators. So it's just a little box that takes a valuation and outputs these bits. And although we call them random score generators, this can be thought as the equilibrium of an implicit game between the agents. Now, once we have these little boxes that translate valuations into bits, we can implement the algorithm I was mentioning before. We just simulate a fake world with valuations v prime. We use these boxes to translate those v primes into bits prime. We set as thresholds the maximum of these simulated bits for each item. And then for each item, we'll just give the item to the first agent whose bit is larger than the threshold. Then the key lemma in our analysis, we call it mirror lemma. And it's basically generalizing the observation we had before for one item. If we look at this green set, Si, where the bits of agent I are larger than 2 copies of the threshold, then we know that the value that this algorithm gets is for agent I is at least half times the value of this set Si. Why? Because we need in the algorithm that the bits beat the threshold T prime and that the items are available. But the items being available is like having another copy, the maximum of the previous true agents, being lower than the threshold T prime. And this is like another copy of the threshold. So it's like being available is the competition between these two IID thresholds T prime and T double prime. And then half of the time, one side is available, half of the time the other side is available, and then because of the subadditivity, we get at least half of the entire set Si. Now, this is true for any transformation from valuations to bits. And then the second part is using the result for the simultaneous first price auction that says that there are bits from an equilibrium that give a constant factor of the optimal social welfare. And then the proof that these bits exist is basically a proof of existence of equilibrium. So it's a proof based on a fixed point argument. So as I said, intuitively, it's like designing an implicit game between the agents whose equilibrium is a constant factor of the optimal social welfare. So in summary, these ideas put together give this 6 approximation that solves this important open question, improves upon this log number of items approximation, and the immediate question we get is, can we do this constant approximation using prices instead of this complicated approach we have as the log number of items does. And the second important open question is, can we implement a constant approximation in polynomial time? Our algorithm can be implemented in exponential time, even though there are these black box, there is a way of doing this explicitly in exponential time. but we don't know if this can be done in polynomial time. So this is an important open question. Thank you very much.